Alright, today's video lesson we're going to review what we talked about in class with respect to taking the derivative of exponential functions. We're going to focus just on the ones with base e for now. The derivative of e to the x is e to the x, which is nice and convenient. But we have to remember that the chain rule is still going to apply. So we talked about a lot of these simpler ones, but I wanted to go starting at m and seeing what happens when I take the derivative of these three functions. In the first case, before I actually take the derivative using the quotient rule, I'm going to remember that if the numerator is just a constant function, it's a lot easier to just use the chain rule by taking the denominator into the numerator and bringing it to the -1 power. That way we can apply the power rule to the outside, and as long as we remember, of course, the -1 times 2 is -2, and then we drop the power by 1 from -1 to -2. The other thing we have to remember is the chain rule says we now take the derivative of the inside composite, which is the derivative of e to the -x plus 1. So here's the inner function. The inner function exists untouched in the first case, and the inner function is then differentiated as a part of the chain rule. Here I'm going to take the -2 power, which is basically taking this base and dividing it, so I'm going to move that down to the denominator, make the power positive, and then the derivative of e to the -x plus 1 is just e to the -x. But here again we've got another chain, another link in the chain, if you will. In other words, right here we have -x, and the derivative of e to the -x has to include the chain rule, so the derivative of -x, which becomes just -1. In other words, we have the chain rule 3 times, 3 links in the chain. So we have the power rule on the outside, so that's why this became -2 and this dropped, and then we have the derivative of the e to the x, and that's just the 0 plus e to the -x, and then we have the chain rule again, and that's where that extra -1 comes from. -1 times the 2, -2, gives us a positive coefficient, and we can also recognize that since this is e to the -x, we can just drop that down to the denominator as well and make the exponent positive. So I can check this with technology, which I will. I just wanted to explore what happens if we decided to use the quotient rule. Totally an acceptable option here, as long as we remember to apply the quotient rule correctly. So remember, it's ho-de-hi minus hi-de-ho over ho-ho. And just to highlight here, this is the ho. So it's, oh, hold on a second. The red is the hi, and the green is the ho, so we have ho derivative hi minus the hi, which is the 2, derivative of e to the -x plus 1 over e to the -x plus 1 squared. The derivative of 2 is 0. 0 times who cares is 0. So that's a nice and easy thing to do. This here turns out to be -2 times e to the -x times the -1. So once again, the chain rule, I had to remember that. And my denominator, which gives me the same exact function that I had over here. It looks like it's fewer steps because I left out a few of the steps with the chain rule here, but nonetheless, we should see the same result no matter which method we apply, if we're applying the method correctly. It's important to graph, and I show both different forms of my solution represent the same derivative that my Desmos calculator gave me. So all 3 of these functions are produced in the graph here, and then the red function is the original given function. We can see how this function is always increasing, first at an increasing rate and then at a decreasing rate. Anyway, moving on, the second function I wanted to explore once again employs the chain rule. So the first thing I do is I take the derivative of the outer function. I bring the 3 times the 1 to get 3, drop the power by 1. Now I'm going to take the derivative of the inside stuff. That's essentially, because this is a difference, the derivative of a difference is equal to the difference of the derivatives. So we take the derivative of each of these separately, keeping the front stuff. The derivative of e to the x, thankfully, is just e to the x. The derivative of e to the -x, as we explored earlier, is -1 times e to the -x. This, then, will simplify to e to the x plus e to the -x. It's about as simple as we can get here. If we start messing around with this, it's just going to get kind of ugly. Of course, I would explore this with technology to see, if this is correct, but I'm going to tell you right now that reference this is correct. But in the interest of time, I'll move on. And this is the one that was most interesting to me, because first thing I did is to use the power rule. I expressed my radical square root as the 1/2 power, and then I multiply the coefficient 1 by 1/2, drop the power by 1, and then take the derivative of the inner function again. That then requires, first of all, that this negative 1/2 means I could actually drop the square root into the denominator. That's the 1/2 is the square root part, the negative is the denominator part, and here's the 2 from the 1/2. So this is just cosmetic. Now when I take the derivative of e to the 2x plus 4, it's e to the 2x plus 4, no problem. But I also have to take the derivative of 2x plus 4 as what the chain rule says. In so doing, I end up with this. The derivative of 2x plus 4 is just 2, and the 2's will divide out. And that leaves me with this. Now, I took the radical back and turned it into an exponent because I started to recognize something. E to the 2x plus 4 is the same base as e to the 2x plus 4. In Algebra 2, we learn the quotient rule for exponents, which says if you divide two numbers of the same base, you just subtract the exponents. 1 minus 1/2 is just 1/2, so this is really e to the 2x plus 4 to the 1/2. And that's when I realized that's the same function I started with. So I've just stumbled upon a function whose derivative is exactly the same as itself. And at first I thought that was mysterious. So I went over to Desmos and I graphed it. And sure enough, when I enter the function square root of e to the 2x plus 4, and then I enter the derivative, I only see one graph appear because both graphs are representing the same thing. I was a little bit mystified until I examined this function further. If you remember your properties of exponents, you see power of a power here. Instead of taking the derivative using the chain rule, if I was being a little bit more thoughtful, I would have distributed the 1/2 into the exponent to produce e to the x plus 2. Taking the derivative of y equals e to the x plus 2 is as simple as getting e to the x plus 2 times the derivative of the exponent, which in this case turns out to be 1, and that's why this function should easily be simplified to e to the x plus 2, whose derivative is e to the x plus 2, as we should expect. Well, thank you again for watching. Have a great day.